All right, ladies and gentlemen, welcome back. I wanted to let you know that your term exam average will be posted the next day or so, as we're just finishing off all the stuff that we had to do with it. I discovered yesterday, though, that you can't go in and review your exam and see your answer and the marks and the TA, the marker feedback. I don't understand why. So that's one of the things I'll be looking into this afternoon. Actually, I have an email into the person who should be able to help me with that, and we'll get that resolved. And so once you can go back in and actually see your exam without being able to do it again, that's the problem. It says that you would be able to do that. I will let everybody know that they can actually log in and see all of the questions, their answer, the correct answer, and the TA notes as to why deductions were made and that type of idea. So that's the only announcement that I have. And once I get that, I'll also let you know what the class average is as well. So. All right, so we, in the context of this course, are just in the middle, or the end actually, of this unit on Equilibria, and we are going to do chapter 18 Wednesday and Friday, today and Friday. We've done a lot of this already. When we were doing chapter 15, I made no distinction on the type of equilibria, and we actually did solubility equilibria as part of the examples in chapter 15. So we've seen a lot of these concepts before. Today and Friday is going to be a lot of calculations, going through and reminding ourselves how these calculations are done so that you get more comfortable with it. These are the concepts that we're going to be going through, and we're going to start with that right now. So to start with, I want to point out that solubility and formation equilibria involve the same entities. These equilibria are competitive in solution. And it really only depends on whether the final product is charged or neutral. If the final product ends up being neutral, then, at least in aqueous solution, you get a precipitate. It precipitates out of solution. If the final product is charged, you get a complex ion that is formed, and a complex ion is soluble and stays in solution. The terminology that's here is a common terminology as you get into more advanced chemistry classes. M is called the central atom or the central entity. It is generally or very often a metal that things attach to, so it's given the symbol M. L is called a ligand, and it's whatever attaches to the central atom. And so if you're taking organic in the future or inorganic chemistry, you will have ligands that are often organic compounds in nature that bind to the central atom in organic chemistry, or the examples we're going to see here, they're inorganic elements that are going to bind, and that would be inorganic chemistry. And as I mentioned, these reactions are competitive in solution. For example, and you actually have the data sheet available to you, and that data sheet has these different solubility and formation equilibria present. And you can see here that the center one, the middle one, produces a solid. That is the solubility reaction associated with lead 2 hydroxide. But lead will also bind with one hydroxide ion or three hydroxide ions to form two different complex ions in solution. And so we have multiple equilibria occurring, and one of the challenges is figuring out which one is dominant, and then if it is dominant, can we ignore the other two, or the other reactions? And a lot of chemistry starts off by going, we're going to make this assumption that only one's dominant. We go do the reaction and it works. Great, your assumption was correct, or it doesn't work, and you have to now figure out how you're going to deal with competitive equilibria. Competitive equilibria is the bane of organic chemistry. You're not going to get 100% product yield because there's other reactions that are occurring. So I decided I was going to show you my demo slide. Normally you don't see these, but on here is the two equilibria that we're going to be looking at. The first equilibria is the solubility equilibria associated with lead chloride, with an equilibrium constant of 5.5 times 10 to the 4. The second one is the complex ion formation with lead reacting with 3 chloride ions, and the equilibrium constant here is significantly lower. It is 24. But this is the demo that we are going to be working on right now. And just give me a second while we go through, and I need to get some PPE on. As you saw the reagent list, I'll be working with lead and concentrated hydrochloric acid. So PPE is important or critical in this demonstration. See, normally I'd get a student to come and help me with this, and they'd be the ones that'd be exposing themselves to the dangerous chemicals. You know, save the professor, isn't that how it's supposed to happen? I think. Something like that. Anyway. Okay, so what we have here is a beaker with a stir bar in the bottom of it, and just so we can easily see the color changes, I'm going to put a colored piece of paper on the bottom and start to stir. And we have some solutions, and so I'm going to start by taking about 50 mils of lead nitrate. And we're going to see in just a little bit that lead nitrate is soluble. Most nitrates are soluble. Just take my stirrer a little bit higher. And now I'm going to add some sodium chloride. And as I add the sodium chloride, if you look really closely, you see a little bit of white cloud forming and then it disappears. There isn't enough chloride actually present to cause the precipitate to form. We actually have an unsaturated solution. There isn't enough chloride to cause a precipitate. It's unsaturated. Now we're starting to see a precipitate. That white cloudiness is staying, and so as I add more chloride, it's just more lead chloride that's coming out of solution. Mix it really well for a second and then turn it off. And what you should be able to see is that the precipitate is forming, clumping up. It's coagulating as in the solution, and it's settling to the bottom. So there is another term, supernatant. The clear stuff on top is supernatant, and you have your solid precipitate down below. Clearly, what's present here in dominant is the PbCl2 precipitation reaction. At this chloride concentration, that's the dominant reaction. Start to stir again. And now we're going to add concentrated hydrochloric acid. And still, as we add concentrated hydrochloric acid, we see the same thing. It's still, nothing's really changing. We just have our precipitate still present. Excuse me. If you're noticing it's getting a little thin, it's thinning out. And that thinning out is that second equilibrium forming the PbCl3 complex ion is becoming prevalent. And we have multiple equilibria that are dominant. And then as I add more chloride, what ends up happening is that second reaction becomes the only dominant reaction in solution, and all you have present is PbCl3 complex ion. And there we have it. Okay. So those are the equilibria that we were looking at. And if you want to see what was happening, this is the slide that shows the lead chloride solubility as a function of PCl concentration. So this is the negative log of the chloride ion concentration. So a PCl of 3 would be 1 times 10 to the minus 3 moles per liter. Remember at the very beginning we were adding small amounts of sodium chloride solution, and it would form a white cloud locally and then it would dissolve again because there wasn't enough chloride to actually initiate the precipitation. We had an unsaturated solution of lead chloride, unsaturated solution, yes. As the concentration of chloride increased, so 10 to the minus 2 moles per liter, 10 to the minus 1 moles per liter, you saw the solubility going down, and by 10 to the minus 1, 0.1 mole per liter chloride, you had solubility that's very low, and that's at the bottom. Once the chloride ion concentration got to be about 10 moles per liter, which is why we're adding concentrated hydrochloric acid, then you're starting to see the solubility increase. And once you factor in activities, you get the solubility, the lead chloride dissolving because of the high chloride ion concentration and the lead chloride complex ion being the dominant entity in solution. There are profiles like this for many, many metal soluble salts, because it's not just one equilibrium that's dominant. Under different conditions, different equilibria are dominant, and we hopefully are working at a point where well, that's one of the assumptions we make, that one equilibrium is dominant, and that's the assumptions we're going to be making here today as well. This is a solubility table, possibly slightly more complicated than what you're used to in terms of solubility, but nonetheless it's a solubility table. The definition by IUPAC for a soluble salt is something that can produce an aqueous solution of at least 0.1 moles per liter. That's not really a high number, but it is what is defined by IUPAC as a soluble salt. An insoluble salt cannot reach a concentration of 0.01 moles per liter. And of course in the middle you have something that's sparingly soluble, which is between 0.01 and 0.1 moles per liter. So as presented here, on the left-hand side are a number of soluble salts, and you see that sodium, ammonium, hydrogen, nitrates, that type of idea, are generally soluble. There are a few exceptions to fluorides, chlorides, lead, being the one present here that we had for demonstration purposes. And so on and so forth. On the right-hand side, the generally insoluble salts are carbonate, phosphate, hydroxides, and of course there are always exceptions to that as well. You don't need to memorize this. It would be given if necessary, but if you want to find out if something dissolves or not, look for the KSP. On the data sheet on an exam, you're literally looking up if there's a KSP value for it, then the salt is insoluble. It's insoluble or sparingly soluble. If it has a KSP, it doesn't want to dissolve in solution. So here we have solubility equilibrium existing, a definition for solubility is that a solubility equilibrium exists when a sparingly soluble entity is put or forms in solution. And the data sheet has a number of these. This is another table with them. They come from the CRC Handbook of Chemistry and Physics, which is a repository of information, and they're just transcribed here. What I want to point out is that on the right-hand side, PbCl2 has a KSP of 1.7 times 10 to the minus 5. That is the KSP of lead chloride. Yet, what I wrote here was that the equilibrium constant for that first reaction is 5.5 times 10 to the 4 with whatever units. Why is it 5.5 times 10 to the 4 here and only 1.7 times 10 to the minus 5 here? I'll give you a few seconds to think about that. Can you explain, both of those numbers are correct. Can you explain why they're different? Go ahead. No, that's would be a huge temperature differential. Actually, it says the KSP on that page is 298 Kelvin, and although I didn't put it here, it's at 298 Kelvin as well. What is the solubility equilibrium look like? We defined it many days ago, but we actually defined what the reaction was for a solubility equilibrium. Does anyone remember what that was? Nope. All right, well, what we're going to do is go over to the document camera. I guess it's a tablet. And to remind you, the solubility equilibrium was that of that. If you go back to that demonstration page, the equilibrium on that demonstration page was how do you get that number right there? You take the inverse, yes. And when you take the inverse of 1.7 times 10 to the minus 5, what do you get? Anyone with a calculator? That'll work. 5.9 times 10 to the 4 liters per mole cubed. When I did this in the first class, I'm like, wait, something's wrong here. Because if we actually go and look at these values, I don't have 5.9 times 10 to the 4. I have 5.5 times 10 to the 4 liters per mole cubed. And so there is, of course, a discrepancy. So this is just an illustrative problem of, William, I know it was minus 5. Yes. 1.7 times 10 to the minus 5. I didn't realize that your exponential was wrong. Okay. Yes, so that's what we have. I just saw your first digits and went, oh, he's gotten it. Thanks for pointing out that you missed it. Oops. So the difference associated with these two values is clearly looking up the KSPs at different times from a different resource and getting slightly different values associated with it. Now, I try very hard to use the same value so all of my results are self-consistent, and this is clearly something that I need to go and figure out what the what the best estimate of the equilibrium constant is. And actually, I will show you in a couple of weeks how to actually calculate equilibrium constant from thermodynamic data. And so that's what I have every intention of doing in short order. So anyway, I just thought it was kind of interesting to point out the fact that there is a difference in the values, and that difference is due to the fact that different researchers publish slightly different equilibrium constants. Hopefully they're slightly different. Not every time it is that way, though. All right. And we already looked at that and that. So here's an example. Here we have the determination of the solubility of zinc fluoride in a pure water solution and in 0.25 mole per liter sodium fluoride. We're assuming, we have to assume that all the dissociated fluorine exists as the F- ion. Why do we need to make that assumption? Before we go in through and solve it, why do we need to make the assumption that the fluorine exists as F-? Anyone? I'll wait. And we have an answer, and it is a correct answer. It's a weak base. Fluoride is the conjugate weak base of HF, hydrofluoric acid. All right. So we make that assumption, and it works at high pH. The equilibrium that we're interested in is this one. So we have our ice table. We need the equilibrium constant, and we can find that off the data sheet. If you look back to that page, you'd find that the equilibrium constant is 3.0 times 10 to the minus 2 moles per liter cubed. Good deal. So this actually is one of the simpler equilibria style problems that you should be able to solve. So I'm going to put you in breakout rooms and give you 3 minutes to set up and solve this equilibrium problem. So you have 3 minutes starting now. You'll be in breakout rooms shortly to share your answers and confirm that you've got the correct answer. How's Shamitha doing?
I'm well, how are you?
Not too bad. I came to a realization that I can't actually go around and help people with, 10 different breakout rooms. Normally in a classroom, people would put up their hand and they're not sure, and I'd be able to go and help them. I don't have that ability here because the ability to communicate with the instructor or with you as well is limited.
But you can go into the rooms.
I can go into the individual rooms, but that's in the 3 minutes I'm giving them to do this. I won't be able to get into all 10 rooms. And neither would, even if we worked together, we wouldn't do that. It's nicer if they put up their hand, then you can go directly to the people who are having a problem, right?
So if they put up their hands in the breakout rooms, are you able to see that?
I don't have an answer for you on that.
Because I know you can see if their microphones are on, but I don't know if you can see if they put their hands up.
That's correct. And I don't even know if I can see if their microphones are on, because according to this, there are no microphones at all active in any of the rooms.
Yeah, I see that. I've had experience before where I've been able to see which rooms are talking and which people are talking in which rooms. So I wonder if you ask them beforehand if they want to put up their hands, if they have any questions, if you're able to see if their hands go up.
Yeah, I might do that again for the
Go
next
into
one,
those
just
rooms.
to learn a little bit more about this. But yeah, it's
Yeah.
somewhat frustrating, because I know the last time there was people that were completely confused, and I can't help them. They're basically sitting there for 3 minutes going, okay, what do we do? And no one has an answer. Whereas if there was people that are able to walk around and provide the next step, they'll be, oh, okay, that makes sense. So I ultimately
Yeah,
have to,
or if could signal to you.
yes, somehow it could signal to me. But like I said, there's no camera, no, sorry, no microphones on at all. So there has to be some people
They could be
talking.
using the chat.
Not sure. So,
Yeah, there's no way to tell.
all right. Well, I'm going to bring everybody back now, and then we'll see if anyone gets an answer. All right, everybody. I'm bringing everybody out of the breakout rooms. All right, welcome back. Does anyone have an answer? Point 2. Other people get something similar? You gonna back up, Kyla? Or do you have a different value? How many people are confused? .17. Interesting. And there's people that are confused. So, yeah, you're going to get .2, Afrin, when you actually figure out what your minor error. Yes, exactly. Kyla is correct. The answer is .2. To very briefly, I'm not going to do it for you. I gave you time to do it. We're not too concerned about the solid. 0, 0, excuse me. This becomes x and 2x and x and 2x. So our KSP equation, of course, is the zinc squared. So when you plug in the values, you get 3 times 10 to the minus 2 is equal to x onto 2x squared, which is 4x cubed. And x is equal to 0.196. Or rounded correctly, it's 0.20 moles per liter. If we go back up here, we have loss of x from zinc fluoride. So when we were asked to figure out what the solubility, this is the solubility. Okay. So that is the solubility of zinc fluoride in pure water. The second part of this was to do the solubility in a sodium fluoride solution. So you have just rewriting the equilibrium. The KSP is unchanged. The ice table is unchanged. 0 and 0.25, because this 0.25 moles per liter comes from the dissociation of sodium fluoride to give you Na plus F minus. So in this second one, you have to do the same thing. And what I would like you to do, I'm going to put you in breakout rooms. I want you to tell me what X is. What is the solubility going through the same process that you just did? So you have another 3 minutes in breakout rooms. And when you come back, put in your answer into the chat, please. One other thing. Could some people, if you do have a question, try raising your hand in the chat. I don't think I can see it, but someone try, or a bunch of people try, and we'll see if we vote doing that. So you got 3 minutes starting now. Go. Oh, Shamitha?
Yes?
I don't know if you noticed, but when I hit the remove to take everyone out of breakout rooms, you could hear their microphones. So people were talking. We're just not able to see their microphones when we're sitting here as in the main room.
Oh, weird.
So, yeah, I was able to hear the communication. They were talking back and forth, and all of it happens all at once. It all comes together, and for about a half a second, you can hear things, and then it disconnects and reconnects them to the main room. So it's just weird that there's nothing visible to us right now. It looks like they're just kind of sitting there doing nothing for 3 minutes.
Yeah, that's really odd, because I remember when I did breakout groups in one of my sessions, I was able to see which groups were active and which weren't.
Yeah, I don't have an answer for you on that. It's one of the limitations. Were you using Blackboard or were you using something else?
No, it was through Blackboard.
Very weird. Well, in this one, the students need to actually use solver or something like that to solve it because the equilibrium constant isn't extremely small and they're stuck with third order polynomials. So, oops. Yeah. I'm sure people are raising their hands and talking and stuff like that, but there's nothing showing up here. So now if I shut this off, you should be able to hear the talking for just a fraction of a second. And I'm doing it now. Oh, there happened to be nothing there, so. All right, now that everyone's back, does anyone have an answer for this exercise? Oh, wow, that was very impressive. Excellent. And to my most amazement, everyone's got the same number. The question is, are you right? What's your confidence level? 100%. No, 100's not the answer, but I'm assuming you're 100% confident. And you are correct. You got the correct values. I'm not going to solve all of this, but just to realize, I'm just going to put in the k expression down here. This ends up being x onto 0.25 plus 2x all squared. And because this is not an extreme equilibrium, this is 3 times 10 to the minus 2, you need to use solver, which you all realized, which is excellent. And you're going to get a value of X of 0.122 moles per liter. And again, that is the solubility. Good job. Good job. Okay. I do want to just go back and now compare these two. This is 0.122 for this one. If I go back to the one before, I get 0.196. Let's look at this equilibrium, and just focusing on this equilibrium, which will show up eventually, what's going to happen to this equilibrium when I add fluoride ions? Which way is it going to shift if I happen to add fluoride ions from NaF? Just from Le Chatelier's principle, which way does equilibrium shift? It's going to shift left. Right, excellent. It will shift the equilibrium left. Well, that is exactly what we saw, or what we see doing the mathematics. Here we get 0.196 with no fluoride initially, and then we get 0.122 when we have an initial amount of fluoride. So all of this should be coming together as a recollection, foggy memories. We talked about Le Chatelier's principle, use of solver, approximations, equilibrium constants, manipulating all of that, doing a lot. All of that's coming together. It's stuff that we've already seen, now being applied to solubility equilibria. The next example that we want to look at is this one. Will magnesium carbonate precipitate from a solution that is 0.015 magnesium chloride and 0.187 moles per liter sodium hydrogen carbonate? And back to the document camera we go. All right. So the equilibrium of interest is that of magnesium carbonate. There's our equilibrium of interest, and we're actually being asked, will a precipitate form? So we're not sure if a precipitate will form under the conditions that we have. And we have, from magnesium chloride, you have magnesium 2+ ions. That's the relevant entity present. And so that gives you, don't do that, 0.015 moles per liter of magnesium ions. The sodium carbonate, I'm just going to actually add plus the chloride, 2 chlorides. The sodium hydrogen carbonate is going to react to give you the sodium ions plus the hydrogen carbonate ions. What is the problem here? Anyone see a problem? Anyone see a problem? Ah, someone typed something. Yeah, the hydrogen. Okay. We have different entities. This is carbonate. I need to worry about carbonate. What I have is hydrogen carbonate. Now, they are related through an equilibrium, but it's not 0.187. That would be green. 0.187 moles per liter. I don't have this amount of carbonate. I have that amount of hydrogen carbonate. And so we need to calculate how much carbonate we have present. And the equilibrium we've got to do that and this is Ka2, 4.7 times 10 to the minus 11 moles per liter. Does anyone else see another problem that we need to think about? There's one more that we need to think about while I set up this ice table. Anyone got something? Maybe? It's not the charge on the carbonate. No, that's fine. Everything's good there. The problem we have is that that's not the only reaction associated with hydrogen carbonate. Hydrogen carbonate, give me a color, is amphiprotic. Okay, it has an acidic and a basic reaction. Now, can we just, and we already, actually, let's back up. We already talked about the fact that we can't ignore the basic reaction when we're worried about the hydrogen ion, because hydrogen and hydroxide are linked together. But because carbonate's not in the other reaction, what we can do is, if we assume, let's give me a color, that HCO3 minus dissociation is negligible in both reactions, if we assume that HCO3 minus dissociation is negligible in both acidic and basic reactions, then we can ignore the basic reaction because it doesn't produce carbonate. This will probably make a little bit more sense after we do this first step. So we're going to assume it's negligible. So the assumption we're making is that HCO3 minus dissociation is negligible in both acidic and basic reactions. What I would like you to do is solve this equilibria. This is a simple acid dissociation equilibria, and solve it and give me x. What is the value for x? And I don't have time to put everyone in the chat. Shouldn't take that long. Just type x into the, sorry, I don't have time to put everyone in breakout rooms. Just type x into the chat. Thank you. And we have a couple people giving answers of 2.96 times 10 to the minus 6 for their value for x. So given an equilibrium constant expression, you get x is equal to 2.96, we'll do 96, times 10 to the minus 6 moles per liter. That's the number I get, so that's good. In terms of checking the reaction, yes, you could go through and check, or you could just compare 10 to the minus 6 with 0.187. And what you find is that, at least for the acidic reaction, that assumption is valid. And as a matter of fact, it's also valid for the basic. But we don't have time to go through and confirm this. Because we are not using up a lot of this 0.187. Basically, so little of it is dissociating to give us carbonate, and so little of it is dissociating to give reacting to give H2CO3, we can ignore the basic reaction. And so this value of X is the number we need for the carbonate concentration. And now I'm just going to go way back up to here and plug that number in. And that was 2.96 times 10 to the minus 6 moles per liter. Oh yeah, and Mark's comment is correct. H2CO3 dissociates into carbon dioxide and water, but that's another equilibrium. That's actually why pop is carbonated and fizzy when you drink it. But that doesn't give you any more carbonate. It gives you CO2, not CO3 2 minus. But good point, good observation. So now we have these numbers, and we're asked, is a precipitate going to form? That means we want to use our initial values to calculate Q and compare that with K. And Q was done the same way as K. And when you calculate those values together, you get 4.46 times 10 to the minus 8 moles per liter squared. All right. I don't have space to do it here. I'm just going to go to the bottom, and I'm going to do that comparison. We have as a number line, K ranges from 0 to 1 to infinity. And, oh, we never did actually look up the KSP. I will give you the KSP here. The KSP is 3.8 times 10 to the minus 6 moles per liter squared. And our value for Q that we just calculated was 4.5 times 10 to the minus 8 moles per liter squared. This is to say Q is less than K. The equilibrium, if it can, would shift to the right. We have no precipitate being formed. We don't have enough present to reach the KSP. So there's no precipitate formed in this system. And that leads to another comparison between Q and K. If Q is less than KSP, the solution is called unsaturated. And we saw that when we were doing the demonstration. When we were adding a little bit of sodium chloride at the beginning, it would form a white precipitate that would then dissipate as the chloride uniformly mixes with the solution. We didn't have enough chloride to start precipitation, so you had an unsaturated solution. If Q equals the KSP, then the solution is saturated and it is ready to precipitate. And that's what would happen if you were to throw the salt in. If you throw the salt in, you instantly will get a saturated solution of that salt because it dissolves to the point of a saturated solution. And finally, if Q is greater than K, you have a supersaturated solution and a precipitate will form. And that's what we saw in the demonstration. When we added enough chloride, we started seeing the lead precipitating out of solution. And that's it for today's class. If anyone has any questions, I can hang around for a bit and answer them on this material. But thank you very much for your attention, and I will see everybody on Friday. When is the Problem Set 4 quiz? Late next week. I don't have a date for you. I'll have a date for you on Friday.